Alright, in this video we'd like to come up with a methodology for finding A inverse. So let's consider some structures. We could certainly solve a system of equations with multiple right-hand sides simultaneously. So let's think about what it looks like for one right-hand side. We would have something that looks like A times a vector x, which is the unknowns, is equal to B, which is the right-hand side of our system. We could then augment that system by putting the coefficient matrix A on the left-hand side of the augment and then the unknown vector B on the right-hand side of the augment. So this is what a typical augment would look like. And so if we had multiple right-hand sides, we just stack those right-hand sides on the right-hand side of our augment. And so we might have something now that looks like A on the left, and then those right-hand sides B1 and B2 would actually form a matrix, which we would refer to as capital B. And so in this example, if I had a coefficient matrix A, which was minus 1, 1, 1, and 2, and then two right-hand sides, namely B1, which was a column vector 1, 2, and B2, which was a column vector minus 1, 2, then I'd be solving for a matrix of unknowns now, X. And so we'd be solving the system of equations A times an unknown matrix X is equal to a known right-hand side matrix B. And we'd simply augment A and B and then solve. So the question is, can we use this to develop a methodology for finding A inverse? And I think we might be able to if we look at it a little carefully here. So if we're looking for the inverse, we're trying to solve a system of equations, A times some matrix X, which gives me the identity matrix, because that is the fundamental definition of what it means to be an inverse. And so that X, if we were able to find a solution to the system of equations, would be A inverse. So what does that look like if we kind of write it out? Well, X is a matrix of unknowns. So each column of X represents the unknown vector solving for each of the columns of the identity matrix on the right-hand side. So we have something that looks like A times the matrix that has x1, x2 to xn as its columns is equal to I, which has as its columns E1, E2 to En, because recall that E sub j just refers to the jth column of the identity matrix. So if we multiply that out, we get n equations that have to be solved, namely that A times x1 is equal to E1, A times x2 is equal to E2, all the way to A times x sub n is equal to E sub n. And so looking at this carefully, we can come up with a way to actually find the jth column of the inverse, because each of the solutions to these n equations will actually form the jth column of the inverse. So for example, looking at the first one again, A x1 equals E1 would actually be the solution that finds the first column of A inverse. So the jth column of A inverse would be A times x sub j is equal to E sub j. So here are n equations to be solved again. And we can write that as an augmented system for Ax equals I, which would be A, the coefficient matrix on the left of the augment, and I, the right-hand side matrix on the right-hand side of the augment. And certainly finding the solution of that would give me X, and if you recall, X is the inverse of A. So we know from before that if A has an inverse, then it must be row equivalent to the identity matrix. So there must be some elementary row operations that will turn the A, which is a coefficient matrix, into the identity. Now you might ask, why would we want to do that? Well, if you think about it, we're trying to solve n equations simultaneously. And so we're looking for a clean way, a straightforward way to do that so that we can read our solution right off. So consider what we're looking to do. If we have A augmented with I, which would give us our inverse, if we could find some elementary row operations that would change A into the identity matrix, then it would be the case that our solution, X, or A inverse, would be what we would see on the right, because this is exactly what it means to turn the A into the identity matrix. So the series of elementary row operations needed to reduce A to the identity matrix are referred to as Gauss-Jordan elimination. And so you've got lots of experience doing the Gauss-Jordan elimination steps. So let's look at the particular example. Suppose A is equal to minus 1, 1, 1, and 2, and we want to find the inverse of A using our Gauss-Jordan elimination. So as a first step, we'll take row 1 plus row 2. That will become the new row 2. So our system becomes minus 1, 1, 1, 0. And then if we add row 1 to row 2, then we should have gotten there a 0 instead of a 1. So that's a typo. That should be 0, 3, 1, and 1. Now we divide row 1 by minus 1, and we divide row 2 by 3. If we do that, we get 1, minus 1, minus 1, 0, 0, 1, 1/3, and 1/3, dividing that second row by 3. Now we take row 2 plus row 1 and make that the new row 1 to finish our Gauss-Jordan elimination steps. Then we get the identity on the left, you see, 1, 0, 0, 1. And then on the right we get first column, minus 2/3, 1/3, second column, 1/3, 1/3. Now before we proceed, let's just think about what we've done here. By doing these Gauss-Jordan elimination steps and turning the A into the identity, now I can actually read X directly, because for the first right-hand side, we see the solution would be minus 2/3, 1/3. And for the second right-hand side, we see the solution would be 1/3, 1/3. So we found the X matrix at this step. So what does that look like? Well, we have on the left, A has been converted into the identity matrix through elementary row operations, and on the right is A inverse. And so we write A inverse is minus 2/3, 1/3, 1/3, 1/3.